slides on the screen. It must be time to start. Welcome to For Butter or Worse, where we will go into excruciating detail about how the graphics architecture in Android works and how we worked pretty hard in Jelly Bean to make it faster and smoother, and tips for how you can take advantage of all of this knowledge that you're going to get to make your apps faster and smoother as well. Before we start...
Oh, wait. Oh. And by we don't mean Chet and I, a lot of other people back at the office.
It's sort of the, it's not the royal we, it's the other we. Before we start, some people may know us for giving out things at the end of presentations, and if that's why you're here, then you should leave, because actually there's a device back in my room at the hotel. So we will not be giving away anything. I just want to be very clear so that the mob doesn't come up afterwards. All right, let's go. So this talk is about butter, and this slide made a lot of sense to us when we created it back in the US. But we are an international platform. We like to localize our experience for the native audience. So it seemed more appropriate for this location. See, now you get it. On the previous slide, you're like, why is there a stick of butter there? And now you're like, well, croissant, obviously. Okay. There are two important terms to understand when we talk about what was called Project Butter and Jelly Bean.
Yeah, we never use the word butter.
No, actually during the release we did use the word jank. The main word was jank, and that's basically a disruptive experience. And there's two elements of jank. One is choppy performance. So if you're swiping on the home screen and you see it stop for a pause and then it leaps forward, you see these sort of little hiccups along the way. That's...
And actually, if you pay close attention to the animations, you know, between the talks, like before the slides are online, you see like all those little spaceships driving by. Those are janky animations.
They actually provided that jank for us to help illustrate the point. It was very effective in kind.
I like that.
And the second type of jank that you can experience is discontinuous experiences. So when you click on something and something unrelated happens on the screen, that's a different type of jank that may also happen. The other term to be familiar with is, of course, butter, or as it translates into French, croissant. So there's two elements of butter. One is having smooth performance. So you've just got this nice, smooth, it feels buttery, basically. It feels buttery. And the other...
I still don't get that.
It's smooth. I mean, we put butter on everything in America. The other is basically the fattening spread that's made us the nation, the growing nation that we are. So there are the two types of jank, but we're only talking about one today. The discontinuous experience is something else that we work on and that you should work on in your applications. But today we're specifically talking about graphics performance related de-janking, because that's what we like to talk about. So there's two main elements to jank and to getting better buttery experiences. Basically, the smoothness and performance of the platform is dependent upon latency, which is the time difference between when something happens and when the user sees the result of that occurrence. So they swipe on the screen and then things start moving. Well, how long did it take between the point where they knew their finger was actually moving on the screen and the point where they see the reaction of the UI elements on the screen to that finger movement? And the other element is fast and consistent frame rate. So it's not good enough to track really fast input if you've got this discontinuous animation where it'll run for a few frames and then it'll stop for a frame or two and then it'll run again, and you've got these hiccups in the middle. What you really want is it feels natural to the user. They are swiping, the elements on the screen are moving at the same speed as their finger. Other animations on the screen are just moving in a continuous motion and feeling natural instead of disruptive. So the elements of input latency are interesting, and input latency was one of the things that people on the team worked really hard on in Jelly Bean to make it much faster and more optimal and more smooth. So it's important to understand how input latency works. Basically, there's stuff going on, you know, deep in the device that is figuring out the hardware part of input. Someone touches the screen, they move their finger on the screen. Somebody down there is responsible for collecting those events. They get batched up and they get put onto a queue somewhere on the device. And then eventually that queue gets processed and those events then get turned into operations that cause us to draw in reaction to those events. So that's, no matter how you're doing this, that's the overall process of how input gets turned into changes on the screen.
So this is an illustration of something that's often referred to as lag, and this is really about input latency. So we have a little animation that shows what might happen sometimes when you drag an icon across the screen. So if you have input lag, this is what you're seeing. The blue dot shows the finger, and the icons you can see lags behind. So we're several frames behind. It's not because we cannot draw fast enough. It's not because the application itself is slow. It's because we're taking too much time to deliver the events to the application. Or maybe we get the events on time, but we take too much time to send the drawing commands to the screen. So if you use a profiler, in this particular example, you would see that everything looks okay. It takes very little time to go through your code. It takes very little time for the framework to do its job. But for some reason, we still have lag on screen.
So one of the big efforts in Jelly Bean was to work on the input latency problem. So you can see there's a diagram of how things happen prior to this work, where you can imagine that there's several inputs going on, the green bar up on the top, these different input events. Maybe the user is swiping across, so it's tracking the motion, basically where the finger is at any point in time. So you've got A, B, C, D, all these separate events there. The dispatcher will occasionally take everything that's in the queue so far and dispatch those things, process them, send them up and say, hey, here's the latest batch of things to process. And then the processing part, the little gray box down there, will process the ones that it's got so far. So you can see in the first gray box, we're processing the events for A to C, which is nice, except you can see we're already up to event G when the processing starts. So you can see some of the sort of built-in latency there. And then finally, we finish processing, and it's time to draw as a result of all this stuff. And then at the end of the draw period, that's really where the user sees the result of what they did at some point in the past.
Yeah, and it's very important to note that this diagram is an exaggeration of what really happens. We never had that much latency on Android. A good latency target is about 4 or 5 frames.
So you can see the result if you want to understand all the different colors and bars on the screen. You can see basically the latency of A is all the way from when the user input the events into the system to when the user saw the result of that. Same thing for C, a little bit less latency because that was input into the same batch as A. And you can see a really extended delay for D because, well, they sent off the batch for C, for A to C, and then D came in immediately thereafter, but the batch was already gone. They had to wait for the next train. And maybe there was a strike. So the event streaming project was about making this process a little more optimal. Instead of having this batching system of occasionally taking everything so far and then chucking it onto another part of the system, we actually do the processing part and grab everything. So there's no dispatcher to get in the way anymore. Instead, when we're ready to do processing, we'll go out and grab everything that's been tracked to that point. So at this point in the processing, which occurs at the same time as on the previous frame, we can grab all the events up to F, which means that F is going to be serviced much sooner than it would be, and also the succeeding events are going to have less latency because now we're able to just get them much more aggressively into the system and respond to them by drawing onto the screen. So frame rate is an important factor, obviously. How fast can your application draw? And of course, one of the obvious things to do, and something that we talk a lot about in our graphics performance talks is, well, just draw your stuff faster. Basically, the less you do, the faster you do it, then the faster the frame rates can be. So yeah, essentially, just take less time to do stuff, and then stuff can happen faster. Sort of obvious. But there's a little bit more to it, which is sort of the point of us spending an hour talking about this stuff today. So we wanted you to understand the architecture of Android graphics. So
that's not a joke diagram, by the way.
Yeah, everybody got it? All right. So let's walk through this diagram little by little. It's a little complicated, but hopefully we can get there in the end. You can think of the rendering system in Android as having essentially these 3 logical blocks. I call this one something happens. User, event, input, whatever. Then we draw stuff. And then Surface Flinger, a separate process on the system, is responsible for taking all this information and actually displaying it on the screen. So for these 3 logical blocks, we can break it down further. So in the something happens, there is an event. The user touches the screen. The user swipes. The user continues motion that was already going. We then set a property value. Let's say we say, okay, we're going to scroll the component by this much. Okay, so we set a scroll property in there, and we invalidate things to tell the rendering system, okay, something has changed in this view, and it's time for you to redraw it with the new information that was changed according to the input event. So then we're into the second logical block, which is drawing. There may or may not be measure and layout that occurs along the way. And after that, we prepare to draw. We basically ask for a buffer to draw into, which is called dequeuing the buffer. So we ask Surface Flinger to give us a buffer so that we have a place to actually put all this stuff. Then we update the display list. We have an intermediate data structure that we use to process all the information about what to draw, and we turn it into this intermediate language that says, okay, here's all the drawing commands, and then later on we turn that into OpenGL commands. So we update the display list, which means draw all this stuff into the display list. And then we draw the display list, so we actually execute those commands, which turns it into then OpenGL commands that get sent to the GPU.
Oh, and your application code is in two places on this diagram. Your application will run in measure and layout, and it will also run in update display list. Update display list is when we call the draw methods on your view classes.
And then finally, in the draw process, we swap the buffers. We tell Surface Flinger, okay, I'm done with all of my drawing information. Could you please put this on the screen? And you have to say please. And then finally, there's the display process, which is Surface Flinger taking this information from this buffer and everything else it knows about the system, all the other windows that need to be displayed on the system, and then displaying the buffer. So it combines all these windows. It's got status bar and navigation bar. Maybe there's a translucent window. There's pop-ups. Takes all this information, combines it on the screen, and then posts the buffer to the screen. And that's when the user finally sees it. So that was this diagram. So now does it make a little more sense, I hope?
So VSync is another very important component to dejanking the system. So the notion of VSync is to synchronize your rendering with the refresh rate of the display. The easiest thing to think about the refresh rate is to imagine that your display refreshes at 60 Hertz. So 60 times per second, the LCD panel will take a buffer from the system and will display the content of that buffer. In practice, not all displays will render at 60 Hertz. Some of them will render at 55. We've had that render at 57. So if your application doesn't quite run at 60 FPS, at 60 Hertz, it's not necessarily a bug in your application. It might mean that you're maxing out the refresh rate of the display. We've actually had this discussion internally where I think it was the Chrome guys were worried because on Nexus S, they were not able to get more than 57 frames per second, but that's the exact refresh rate of the display. So there was no need to try to optimize the code more. They were blocked by the display itself. And the reason why you cannot draw faster than the display is for something called tearing. So if you've played video games on PC and on consoles especially, you might have seen this little artifact where if you move suddenly, like if you turn around really quickly in your game, you will see this little vertical bar in the middle. That's what we call tearing. So that happens if you do a swap buffer, if you send a new buffer to the display, when the display is halfway through reading that buffer and updating the pixels on screen. So to avoid that issue, we do VSync. So we listen to VSync and we wait until the display is ready to display the next frame before we give it a buffer. But that's only for correctness. So here you have, well, we talked about that already. Actually, yeah.
This is leading into the next topic.
Yeah.
So yeah, the point of VSync is to basically get everything prepared and then post the buffer to the screen. So we don't have tearing on Android. There's other platforms that I've worked with in the past that have tearing just because there is a disconnect between the vertical retrace system and the rendering system of the platform itself.
And to be clear, we've been using VSync since Android 1.0 to avoid tearing, so that's why you've never seen that artifact on Android. But there is more to VSync than just the tearing. So yeah, we already use VSync to give you a non-tearing experience, but now we actually use a VSync as of Jelly Bean to give you a smoother performance and smoother feel by basically synchronizing our own internal rendering to when the VSync happens. So let's understand a little bit more about what's going into it first. The CPU gets involved in the rendering system. Basically, when your code gets called to say, you know, how do you want to draw this custom view, or our rendering code does, you know, draws the button or a list view or whatever. And we turn this into then commands that tell the GPU how to do its job. So we're going to turn the Canvas API commands like draw a line into an OpenGL command to draw a mesh or whatever.
And then we also use the GPU to display it on the screen. So we pass it to Surface Flinger sends some commands to the GPU, and everything appears on the screen. And then the yellow bar at the end is the happy user finally seeing the results on the screen. So if you're drawing without VSync, and again, this is not the tearing VSync, this is the, I don't know when VSync is happening, I'm just rendering whenever I can.
This is what was happening on Android until Jelly Bean.
Right. And exactly like this, too. Everything was in green and blue boxes. So the yellow bar at the top shows the number of the frame that's currently being displayed. So we're displaying frame 0, and in the meantime, the CPU is working on buffer 1. And then when it's done, the GPU can work on buffer 1 and output commands to there. And then on the next VSync, the display will pick up buffer 1, and it will display that while we're working on buffer 2. But the problem is jank, because we started working on buffer 2 so long into the next frame that we weren't done with it by the time the display was actually ready for it. So the display had to pause there on frame 1, and the user sees jank. They see a pause there because they're still seeing the stuff that they saw on the last frame because we just weren't ready for it yet.
And it's not exactly a performance issue. It's not that the code is going too slowly. It's not that we're using the GPU too much. It's just we scheduled the work at the wrong time. So it can be very difficult to profile, because if you use a profiler, you'll see that your code is running very quickly, but still you will see that jank on screen.
So by synchronizing more closely with the vertical retrace system, we can basically execute all the rendering commands at the beginning of a frame instead and give ourselves a much better chance of finishing this stuff by the time the display needs it. So this is the same timing information as we had in the previous frame, except that everything is able to start sooner because we get this nice heartbeat pulse from the system that says, hey, I'd like to do the vertical retrace now. Go ahead and do your rendering. So in particular, in the second section there, you can see that we're operating on buffer 2 much sooner than we did before, and we don't experience that kind of jank here. Display lists are an important component. I mentioned them earlier in how we work with the GPU. So we turn all the rendering commands at the SDK level into rendering commands at the native level that then get turned into OpenGL commands. So we've got this sort of intermediate command and argument language and data structure that we use. So when properties get set onto views, let's say an alpha property if you're fading it in or out, or a translation X, translation Y property moving around on the screen. These cause invalidations in the system, which means, hey, this view just changed, please redraw it. That will result in a drawing command later to find out how to redraw that view. We update the display list for that view, so we change the display list data structure, we redo all the drawing commands for that view, and then we draw the display list to the display, to the GPU through OpenGL commands. All of that works pretty well, but there's a fair amount of work in updating the display list every time around, every time one of these simple properties changes. So we did an optimization in Jelly Bean to say, you know what, actually the view itself didn't change, only one of these handful of properties changed, and I know how to do that much more efficiently. So instead of recreating the display list on the fly, we can simply update the value of this property that the display list needs, and at the time when the display list goes to render, it will just pick up the new value of alpha, translation X, whatever, and we basically skip that entire step of drawing at the SDK level, and we can just execute some pretty quick native code and turn it into OpenGL, and away we go. And we can also do it much closer to the VSync pulse. So display list properties was that project, and basically if you're working with one of these handful of properties on views, then you're going to get that performance for free, and that's how we get a lot of the performance and smoothness and smoothness improvements in things like Launcher and the built-in applications that we have. So you can see some of the timing results here. Bigger is worse, and essentially we took the processing time of display list down to essentially 0 because they're not being recreated anymore. They just render with the new properties. Parallel processing and double buffering. So we did double buffering up until Jelly Bean, and double buffering is a good thing to do. It means the display can be showing one buffer while the rendering system is dealing with another. And then when the rendering system is done, they swap, right? Pretty good system in general. However, you occasionally get jank. Because things may not happen as fast as you want them to. Even if you're syncing at the right time, if you take a long time to do stuff, then you may cross a frame boundary and get jank. So this is in a good system. We display A, B, and we're working on the other buffer in the meantime in the rendering system. All of that is good. But in this case, we took so long to draw in that first frame that we skipped a frame and we get jank. And then we come around and we do it again. The next time we have to wait for the next vertical retrace to start the next rendering. And again, we took so long that we janked again. So 2 janks in a row, bad.
And so what happens when you get those janks that your application is running at 60 frames per second, then you fall down to 30 frames per second, then you might go back up to 60, then you go back down to 30. And that's usually the cause of what you see as jank on screen. You see like an inconsistent frame rate. We keep going up and down between 30 FPS and 60 FPS.
So in Jelly Bean, we moved to a triple buffering system on demand. So there's still going to be a situation where we may take longer to draw than we have available in any particular frame. And that may cause a frame of jank as we realize that there's a problem. And then we can introduce a new buffer into the system. So here, again, on the first frame, we took so long that we crossed the frame boundary and the display didn't have anything new to display, so it janked. But then it said, oh, you know what? A third buffer would help in this situation. So now we can start working with buffer C, and the display can be working on buffer A, and then there's always another buffer available to be used in the system. So that second jank didn't happen because we increased latency, so the time between actually rendering to buffers and displaying them on the screen may have increased, but we didn't cause a pause for the user waiting for something because the display simply didn't have a buffer available to show.
So we talked a little bit about window composition. So Surface Flinger is the module on Android that takes all the windows visible on screen, gathers them together, and puts them on display. You'll see, so very soon we're going to talk about what you can do in your applications to optimize the application and what tools you can use to combat jank. And to understand one of these tools, you have to understand exactly what Surface Flinger does. So we have 2 ways of compositing all the windows together. We can use the GPU, so that's what we, those are the blocks on the left when they say FB, it means frame buffer. And that name FB and overlay, they will be important later. So we can use the GPU to composite everything, or we can use something called the overlays. So when we use overlays, we use a dedicated piece of hardware. It's not the GPU, it's something else. And those are essentially free for us. When we have to use the GPU for window composition, the GPU is busy doing work, so the app does not have access to 100% of the capabilities of the GPU. So ideally, we want to do all the window composition in the overlays. The problem of overlays is that because they use dedicated hardware, we have a limited number of them. So on most devices, we have 3 overlays or 4 overlays. So if you have too many windows on screen, we have to do some of the composition work with the GPU. We flatten everything into an overlay, and then we use the other overlays we have to get the final result. So the first tool I want to talk about is called dumpsys GFX info. If you've never used dumpsys before, just run the command on your phone called adb shell dumpsys, and you'll get a list of all the services that you can query. And there's a lot of extremely useful information. This is basically where we spend most of our time when we debug applications. We look at those ADB bug reports that contain megabytes of logs from the device, and a lot of them come from dumpsys. So dumpsys GFX info will tell you how much memory your application is using with hardware acceleration. So you'll see like how many textures you're using, how many views you have on screen, things like that. However, it can also be used for profiling. So if you go to developer options, and on 4.2 you have to remember to enable them with the little tapping the build number 7 times trick. There's an option called Profile GPU Rendering that we've added in Jelly Bean. So you have to turn that on, and after you turn it on, you can query your application. For profiling data. So I'll show you an example. So we'll switch to the terminal, and on this phone here, I'm just going to go to the settings application. So one of the built-in applications, I'm scrolling the list, so you would do that with your application, you just interact with the application. And then when you call dumpsys, the other one, here we go. So you call dumpsys GFX info and you specify the name of your process. So here com.android.settings. When I run that, oh, of course. All right, sorry about that. There we go. So we get a dump with a lot of information in there. So these are this is the memory usage that I was talking about. But what we're interested in is the profile data right here. So what we do is we record the last 128 frames that your application draws, and we dump the timing values in dumpsys. So if you switch to a spreadsheet and you just paste that data, you can select it and create a beautiful chart. So usually I like to use stacked columns. And this will give you the timings of each frame. So let's make that bigger. There we go. So this is what it looks like usually. And you can see that in this particular case of settings, most of the time we're taking less than 7 milliseconds to draw a frame.
16 is an important number to keep. Is an important number to keep in mind. If you want to hit 60 frames a second, you have to draw in less than 16 milliseconds. Not a lot of time.
So there are 3 parts to a frame. The blue part is update display list. So that's the time we spend in your code executing the draw methods of your views. So if the blue bar, if the bottom bar is the highest, then you should optimize your Java code. You might be doing too much work. There might be GC pauses, things like that. The red part is what we call process displays. That's the time we spend in the framework taking your drawing commands and translating them into OpenGL. So as part of this process, we might have to create textures, upload textures. So it's not directly linked to your application code, but if you do something bad in your application, like you create a new bitmap on every frame, we might spend too much time in process displays because we have to do more work than necessary. The last part usually will be very small. It's called swap buffers. It's simply the time it takes for us to send the buffer to Surface Flinger for window composition. So here you have an example of an app that behaves extremely well. Every frame is under 16 milliseconds. So if you want to quickly profile your application, that's a very good way of doing it. And with 128 frames, you get about 2 seconds worth of data. Yes, there's a question? What is the swap buffer variable? It can depend on many things. It can be the scheduling of the device. Sometimes we ramp the CPU up and down. We can be waiting on the GPU. But usually you don't have to worry too much about it. The next tool we want to talk about is something called systrace. So systrace is a new tool that we introduced in Jelly Bean. It's part of the SDK, and it's a tool that lets you inspect the whole system at any given time. So how many of you have used TraceView before? Okay, just a few. So TraceView is our profiler. That's what you use to profile your Java code, but it can only inspect your own process. Sometimes that's not enough to understand what's going on, so we have this tool called systrace. So to enable systrace, you have to go to the developer options. There's an option called enable traces. When you click on it, you can choose what kind of traces you want to see. So here, what we're doing is we're enabling graphics and view traces. And these are typically the options that you want. Once you've done that, you might need to restart your application to make it work. So I have a little demo. I wrote a simple app. It's just a simple list view. But when you scroll the list view, the performance is pretty bad. And we look at what happens in systrace. So running systrace is very simple. You just need to run that script systrace.py. And I'm just scrolling the list view right here. So systrace is going to capture a few seconds worth of data, and it creates an HTML file. Now we can open it. And this is what it looks like. Okay, so there's a lot of data here. There's a lot of very interesting things. For instance, here, if we look at the top, we can see that 2 CPUs were busy. This is a quad-core CPU, and 2 cores were actually doing work. And if I zoom in on the CPUs, you can see the name of the processes that were scheduled. So here, for instance, you can see my application called SlowList that was running in parallel with Surface Flinger that's busy drawing on the screen. So there's a lot more information in there that you might not need. The part that we're interested in is right here. So this is the name of my process. And if I zoom out, it's usually a good idea to zoom out to see what's going on. And if you look at those, so those purple bars, it's called draw. That's when we're drawing. And if you look at where the purple bars are, you can see that we're not consistent. We don't have a consistent frame rate. There are gaps between those bars. So if we zoom in on one of those gaps, we see that we spend a lot of time, in this particular case, 52 milliseconds. We're spending 52 milliseconds delivering touch events to the application. So, and if we look at the draw time, we spend about 15 milliseconds drawing, and here 4 milliseconds. So the drawing is fast enough. The problem is that we're doing work between the frames, and this is where the application is stalling, and this is why the application looks bad. And if we look at what's happening here, I think I can zoom in, yeah. So at the top of every bar, you have those little rectangles, and they indicate whether your process, your thread, was running, or whether it was idle, or whether it was sleeping. In this particular case here, we see a lot of white, and white means that your process was sleeping. It was waiting on another process. So we can look at the top at what the CPUs were doing, and we can see that when we are sleeping in our process, we have something called a binder that's scheduled on the CPU. Our application is not doing anything, something else is. The binder on Android is our IPC mechanism. That means that we were talking to another process. We were waiting on another process doing things. And if we go back to the application and we use TraceView this time to look at what the application is actually doing, I'm not going to run it again. I have a trace that I took just before the talk. Here we go. So TraceView, a very similar tool. We know that it was happening between that something was happening with the binder between the draws. So if I look for a draw method, there we go. So we can see those gaps here as well. So if I click on one of them, I look for the parents, content resolver.query. So we're basically doing a database query too often on the UI thread, and we're blocking the UI thread. We're preventing the application from running. Don't worry too much if you were not able to follow what I just did on screen. Using those tools takes time. You need experience to be able to use them properly. But if you have not used them, start doing it. If you have performance issues in your applications, use TraceView and use systrace. That's what we use pretty much every day to solve all the performance issues that we run into on Android. And this is the two tools that we used, especially for Jelly Bean, to make it smooth and fast. So just to recap, systrace by default will capture 5 seconds of your application running. You can tweak that. There are command line arguments that you can use to change that value. And we output, that's very interesting, the output is a standalone HTML file, so you don't need a special viewer. So you can attach that file to a bug report, you can send it to your coworkers. It's a very easy way to pass the information around. Another tool I want to talk about, so it's another DumpSys tool, it's called Surface Flinger. So that tool will tell you exactly what's going on at the composition level. So remember I told you that we have a limited number of overlays in the system, and DumpSys Surface Flinger will tell you if you are using these overlays or not. So I'm going to skip ahead. Okay, so if you run DumpSys Surface Flinger, actually, just to give you an idea of what it looks like. Again. Okay, this is what dump surface flinger looks like. There's a lot of information, a lot of it you don't care about. But if you go at the bottom, you will find this table here. It's a little hard to read because of the font size. But that's what I'm going to show you on the slides. So here's an example of what the table looks like. You have a type of buffer on the left, and on the right-hand side, you have the name of the activity, the name of the buffer. Everything in the middle, you don't really have to worry about it. It's information like the size of the window, whether we're blending it or not. So if you are in a good situation, everything is in an overlay. That means that the GPU is entirely available to the application, to your application. So this is what you want to see. If you are not in a good situation, you will see that some of the windows will be put in FBs. So remember, when FBs are frame buffers, that means we're going to use the GPU to take the 3 buffers and turn them into a single overlay. So that's what you don't want to see.
I think FB was renamed to GLES.
Oh, okay, where you
in 4.2. So if you're running on the latest release, that may say GLES. Like the output you were just looking at said GLES.
There you go.
Yeah.
GLES or FB. That messed up my slide.
What you will see will be nothing like this.
Yes, but very close.
It will remind you of it.
So there's a couple of things you have to be a little bit careful with the DumpSys Surface Flinger. So first of all, try to run it only while the application is drawing, because we have a special optimization for power usage reasons when we're not drawing anything, we're going to capture everything into a single frame buffer, and the output won't be really correct. So make sure that you run it while your animation is running or while you're scrolling. And also the number of overlays, I mentioned it before, depends on the device. So don't try to use at least a couple of devices, but usually a good target is 3 or 4. So don't try to have no more than 3 or 4 windows on screen at a time. If it's very important for you to have access to the GPU, if you're doing a lot of heavy drawing, if you're doing, if your screen only has buttons and checkboxes, you don't need to run at 60 FPS, so that's not a big issue. So we talked about trace view. You should definitely use it. It's very easy to use from ADT in Eclipse. There's a little button that says start profiling and then stop profiling, and you will get a trace of what your application is doing. Hierarchy viewer, how many of you have used that tool before? Not many. Well, that's bad. You should use it. It also gives you profiling information. It will tell you how much time it takes to render your window in software, how much time it takes to measure and lay out your views. So if you have performance issues and you think they're related to views, you can use this tool to fix them. It will also show you the entire view tree, so you can try to optimize it by removing views or flattening the tree. Unfortunately, Hierarchy Viewer doesn't work out of the box with your devices. If you bought a device in a store, it works with my devices and Chet's devices. So I created this little project on GitHub called View Server. It's a simple class that you can drop in your application. You have to add a couple lines of code to your activities, but they will let you use this tool with your application. So go check it out. The license is Apache 2, so you can do whatever you want with it. It's really useful. Tracer for OpenGLES is a tool that we talked about earlier this week during our university session. It captures all the drawing commands that we send to the GPU, and it shows them in the view with a view tree. So you can see exactly what the application is doing, exactly what you're drawing. You'll get timing information, so it's an easy way for you to understand like what views are taking a lot of time to draw or not. And also, it's pretty cool to watch that tool. It's part of the SDK, of course. Allocation tracker, it's part of the DMS. How many of you have used that one before?
Oh, very important tool.
I feel like I'm talking about this tool every year, but apparently I need to keep doing that. Allocation tracker is part of DDMS. There's a tab called Allocation Tracker. You select your process, you click Start Tracking, you play with the app, you click Get Allocations. It will give you the stack trace of every single allocation you make in your application. So if your application is doing a lot of GCs, especially while you're drawing or animating or scrolling, this is a very good way to figure out why you're GCing, because it's due to the allocations. So you should definitely use it.
I use that as well as the JHAT or matte tool recently to debug a wallpaper that I found on the Play Store, and basically saw that while the wallpaper was running, I was constantly getting GCs, really huge GCs, and they were causing significant performance hiccups in the app. It was a really awful experience, but it's very easy to use Allocation Tracker to figure out, well, where are these allocations coming from and why.
So here are the different things you can do to deject your application. You want to get a consistent frame rate, you want to lower latency, you want faster display list drawing, you want faster display list updates, and you want to avoid window composition on the GPU. So to achieve that, so how many of you have used this keyword before? Really? Everybody should be raising their hands. Well, stop using it. Ideally, I would want to see applications that never ever allocate anything. More seriously, try to avoid allocations in performance critical methods, so in draw, in measure, in layout, when you deliver touch events, any type of code that we're going to invoke a lot on your behalf, any allocation will hurt a lot. So first of all, creating objects is pretty expensive because constructors usually do a lot of work. And then when the GC triggers, we have to pause the application. So if the GC triggers while you're scrolling or animating, you're going to have stuttering, you're going to have jank. And this is where the allocation tracker becomes extremely useful. So for consistent frame rate, avoid allocations.
So it's clear to be, it's nice to be clear here. It's not that we expect you not to use objects. We use them internally as well. But for instance, there's a distinction between when an animator starts and animator allocates the objects that it needs to track the information during the animation. And when the animator is running, it's the is running thing that's really important. Don't do the allocations in your inner loop. In the middle of your animation, if you're allocating things, you will cause a GC at some point that will cause performance problems.
So the next tip, there's a lot of code on the slide, but the point is that avoid doing too much work. It seems dumb, but we see a lot of applications that have performance issues. It's just that they are doing too much work, and most of the time they are doing the same work over and over and over again. And this is where tools like TraceView and systrace will be extremely useful to identify the bottlenecks and figure out what code you have to optimize. Removing code usually will lower latency and improve frame rate. We introduced a new API in 4.1 called the choreographer. So if you're doing your own animations, if you're doing your own rendering using a surface view, for instance, with the canvas or OpenGL, you will want to use choreographer to VSync your animations. By default, we won't do it for you because it's your own thread that's running. So we have this new API. We talked about it. We had a more complex example earlier this week during our university talk. There are some convenience methods. For instance, on Vue, you can call post invalidate on animation that will ensure that your invalidation is synchronized with the display. You can also post callbacks. So if you're doing your own rendering, you can just post a runnable at the next VSync, or you can use the choreographer directly.
There's another API that was also introduced in 4.1 called Time Animator. It's another way to synchronize with the refresh system and get your timing pulses on the same timing pulses as the rest of the animations in the system.
Layer types. This is a new API that we introduced in Android 3.0, I believe. When you set a layer type on a view, we're going to take a capture of that view. We're going to capture the view either in a hardware texture on the GPU or in a software bitmap, so you can tell us what you want. This is extremely useful during animations or scrolls. If you have a very complex view, a view that takes a lot of time to draw, before you if you animate that view, on every frame we'll have to redraw, to re-execute every single little drawing command. For instance, if you have a chart, you might have hundreds of little lines that we have to draw. If you put the view in a layer, we're going to draw the view once into the layer, and then we're only going to animate the layer. So we have a lot of optimizations for layers, and they're extremely efficient. If you're using layers consume a lot of memory, so you have to make sure that at the end of the animation or at the end of your scroll, you get rid of the layer. The best way to do this is to use the new view property animator introduced in 3.2, and there's a new method called with layer that we introduced in 4.1. So with layer will take care of everything for you. At the beginning of the animation, we'll create the layer. At the end of the animation, we're going to get rid of the layer, and you have nothing to worry about. Clipping is another very important way, very interesting way to improve performance. So if you've done your own drawing, if you've ever created your own custom view, you've seen this API. So view.invalidate is how you request the framework to redraw the screen. There's a variant called invalidate as well, but it takes a rectangle. So you can tell us what part of the screen you want us to redraw exactly. It's very important to use it, and this is why. So let's imagine that we call view.invalidate in one of our views. What's going to happen is we're going to traverse the tree of display list, and we're going to ask every single one of them to update and redraw, because you're telling us to redraw the entire screen. If you call invalidate with a dirty rectangle, we're going to only execute the display list that intersect with that rectangle. So we're able to avoid a lot of work. And this is what we do in a lot of our applications to ensure high performance. A great example is a text view. When you have an edit text field where you can input text with the keyboard, we have this little blinking cursor. It wouldn't make sense for us to redraw the entire screen every time the little cursor blinks. So we have code that says, please redraw only the part of the screen that contains the cursor. And this is a great way sometimes to just make your application go really, really fast. Oh yeah, and if you want to debug invalidates, if you know that you're calling invalidate in your application, you can go to developer options. There's an option called show GPU view updates. It will flash the part of the screen that's updating in red. So just use your application, and if you see the entire screen flash red all the time, you're probably doing something wrong.
So this is an interesting one that we ran into with an application that we were trying to optimize where,
Google Now,
for instance,
on screen.
let's say the application was called Google Now. They have a card-based view system where they display these cards of information, and they're stacked on top of each other, and they don't just look like they're stacked on top of each other. They are stacked on top of each other, and each one of these cards is potentially very complex, drawing a lot of stuff behind there. And we were seeing a performance problem because they're rendering a bunch of stuff into a card, and then they have this other card on top of it that renders a bunch of stuff, and then another card. And the only thing that was visible on the cards in the back was the little header bar, right? So at that point, you're like, well, why are we wasting all the effort drawing the stuff behind? So there's some tricks that you can use to optimize in your application. We can't do this in the framework. We just draw what we're told to. We don't know what's on top and what's behind, but you do. Your application can actually optimize for this. So in this case, we knew that when we drew that first one, yeah, that may be all the information that we need there. But then we have all this overlap of basically we shouldn't have drawn that area. So we can say, well, maybe instead we should actually clip rect this thing. We can say, okay, well, when you draw this card, I only want you to draw stuff with this within this region. And then when it gets down into the rendering code, then we can say, well, I'm about to draw a line or, fill a rect or draw some text. Oh, you know what? It's not inside the clip rectangle. No op. Very cheap, very fast for us to handle. We love doing nothing. Very lazy programmers.
Yeah, actually sometimes we optimize so much that apps don't draw anything, and usually our boss gets mad at us.
But they are really fast.
It's a really fast black screen.
So essentially you set a clip rect on the region that you know is going to be visible, and everything else gets clipped outside of it. So we only drew that part at the top for the card that was in back. Much faster display list drawing because we didn't have to draw that stuff. That's the user code. That's your custom view code or our view code that's getting skipped entirely because, hey, not inside the clip rect, don't care. Another way to do the same thing is to do a quick reject on the canvas. So you can actually do this check yourself. So I think this was actually the approach that Google Now took, not just set a clip rect on this area here, but they didn't even tell us to process anything for much of the larger and more complex stuff. They just said, you know what, if this big block of information is not within the rectangle that I know is going to be visible, reject. And then it never even got into the display list. Dim layer, this is interesting. This relates to the frame buffer versus overlay thing that we were talking about before with the hardware compositor. So as Romain mentioned, when you have multiple windows on the screen, if you have enough windows, then the Surface Slinger may be forced into a situation where it needs to use the GPU to draw some of those windows, to blend some of those windows together. And we ran into this with an application that was using a dim layer. Dim layer is kind of a nice UI effect. If you want to focus on a piece in the middle, you can dim everything else out. It helps focus the user's attention. Great UI experience, but in this particular case, they were running an animation inside the view of this thing that was popping up at the same time as the dim window was coming up, and because of the hardware compositor situation, it actually caused a fair amount of jank because there was simply too much that was happening on the GPU simultaneously. So if you want to use a dim window, then you can use the flag dim behind. And then you'll see if you use dump-sys Surface Slinger that it actually shows up as a separate window. It's a separate piece of information that Surface Slinger needs to deal with and hardware composite together. And that dim animator basically forced the system into having several of the windows become FBs or GLES surfaces instead of overlays. So now all of a sudden the GPU is really busy doing this other work. Not what you want. So instead, it was an easy workaround for the application. Once we found it by using things like systrace and traceview, once we figured out what was going on, remove that thing, don't do a dim window, but actually just have the application itself be a full screen window that dims the area behind it by simply setting a background color that was partially translucent. We had the same visual effect, but we removed the problem from the GPU that we were having. Faster display list drawing, less to do, and less collision in the GPU about everybody trying to do too much all at the same time. So I think the final message that we have for the talk is that users, even when they get their butter through croissants, love butter. So spread the word. That's the talk.
They didn't get the joke.
They didn't at all. They're taking notes. They're like, croissant, butter, spread. Okay. I think we have, thank you.
Yeah.
We have 7 minutes to not give
questions.
away
Yes,
devices,
nothing to
but we have 7 minutes for questions. Yes? There's a difference in the approach. The dim layer is actually a separate window, right? So that's what caused the problem. Was it's an entirely separate window being created by the system to be put behind the application. We can't do that automatically because, well, the application told us to draw a pop-up that's only that big. So we can't automatically put, you know, a window behind that. That drawing is up to the application how it wants to draw itself. So it was an application change. It wasn't something that we could handle at the framework level. You can either use a separate window or you can draw your application differently. It's up to you.
If you do clipping, do you manage the dimensions yourself, or how you deal with different device sizes?
So if you do clipping, how do you deal with different device sizes? It's pretty easy. Every time you do clipping, so when you call clip rect on the canvas, make sure that you use that you don't hardcode values. So you have to use the dimensions of the view. So you can use get width, get height. You can call get left, get top to know the position of the children. So make sure that you use dynamic informations about your items. If you're interested in seeing how the UI toolkit does it, you can go look at the source code of Android and look at the class called view.java. And we have two draw methods inside. And if you look in there, you'll see that we call clip rect, and it only uses values that come from APIs like get left, get top, get width.
Yeah, it's important to understand the distinction between when you need to be aware of different device configurations and when you're actually in your runtime code. So you need to use different drawable assets and different ways of laying out your application depending on orientation and size and all that stuff, so that we know how to lay things out. But once things are laid out at runtime, you can query the width and the height and the left and the top, and all of that will be in pixel values. And at that point, you use those to determine how to clip appropriately.
Yeah, you'll see that in practice, it's very easy to do. No more questions? If you have questions because you're too shy or you don't have any right now, we'll be at the Google booth this afternoon for a while, so drop by and ask us questions.